So what else do we have? We have population growth. It's almost summer, so we could do that problem. We could say during the first week of June, a biologist determines, somebody's got to do this job. There are 200 mosquitoes in a particular area. And the first week of July, there are, let's go with 500 mosquitoes. How many will there be in the first week of August? All right, so it's 2 months later. Okay, because we're gonna set time in months. And let's see, when will there be? I don't know if this is going to be on the same level, but let's say when will there be? Okay, that may not happen because if it's like in October, then it's not going to work. Okay, but we can figure that out. Okay, so we're going to say there's a biological growth, right? P of t, population at a time, is equal to your initial population, e to the r times t. Okay, that's the model we're going to use. Okay, so in the first one, right, we went t was 1, right? And when t was equal to 1, the other next information I have, July, 1 month, right? We have 500 is equal to 200 e to the r, and then t was 1. All right. So we're going to say this is going to be 500 over 200, right? Because we're just going to divide. That is equal to e to the r. All right. And then we'll go ahead and hit a logarithm. Oh, let's not do it that way. Let's say take logs of both sides. That's something that one of my other classes kept doing, was they would write, something like 7 times log, and they wouldn't write anything after it. Like, it doesn't work that way. It's like writing 7 square roots. Like, you got to put something in here, okay? So it's never log, it's log of something. Okay, so don't just let it go with a log, just put something in there. Okay, and next semester, when you take trigonometry, you're going to learn 6 new functions, sine, cosine, tangent, but they're going to harp on you for the fact that it's got to be sine, S-I-N-E, sine of something, tangent of something. It's not just sin, right? That's a religious term, sine of. Okay. So our r, right, is equal to, we have e to the r was equal to 5 halves. The zeros will cancel. And then take the log of both sides, ln, not log, ln. So this comes down in front. So we have r, ln e, you don't really have to write that, is equal to ln 5 halves. Okay, so there's our value. So our r for mosquitoes is ln 5 halves. Okay, I usually just note that I know it rather than try to carry that decimal around. But there we go. Okay, how many will there be the first week of August? Okay, so when time, right, equals 2, we get, well, I don't know what this is, but I know what this is, I know what this is, and I know what that is. So that's going to be, right, 200 e this is going to be ln to the 5/2 times 2. Okay, don't put the 2 in here. It's a little different. Okay, and this is equal to p of t. Okay. So to put that in the calculator, okay, we can massage this a little bit. We could say this is 200 e to the 2 times ln 5/2. Okay, that might be a little bit easier to type in. We're going to say this is 200 times second function ln, 2 times ln, and they have a third parenthesis, another parenthesis in there, so the 5/2 goes in there, and then we'll close that parenthesis, the first one. Okay, oh, cool. So 1,250. All right. So they asked us when there's going to be 1,000, right? When will there be 1,000 mosquitoes? Yeah. So somewhere between July and August, I mean, clearly, but when will it be? Okay. Okay. So we're going to put the 1,000 in because that's the P of t equals P of 0. That was 200. E to the R, right? E to the R, which is 5/2. And we don't know what t is now. So let's go ahead and clean this up. So we're going to divide both sides by 200. So we have 5, right? Because these cancel. So 10 divided by 2, 5 is equal to E to the ln 5/2 t. Take the natural log of both sides. So we have natural log of 5 is equal to natural log of E. If you want to keep this as RM, wait for mosquitoes until you put it down and get ready to calculate it. That's probably for the good, right? Otherwise, this gets confusing. We're going to pull this stuff down in front. So we have natural log of 5 is equal to R sub m times t. Natural log of E, which is 1. And now we're just going to divide by my rate for mosquitoes. So time is equal to, this is ln 5 over, what did we say ln? That's ln of 5/2. Okay, so we just type that in the calculator. Natural log of 5 divided by, don't forget your parentheses, 5 over 2. And remember, this is a change of base formula. This is not telling us anything spectacular. Okay. So t was 1.7, technically 76, but like 1 month and 3 weeks, right? Because that's 0.75 of 1 month and 3 weeks is equal to time. Okay, so that would be a population growth problem. All right, those are always fun. Let's see. Do my other one. I have the same problem, but so Bloomsburg University, it's in the middle of Pennsylvania, has a lot of chipmunks. So say in fall of 2020, there were 100 chipmunks on campus. I mean, I know they look very cute when they're by themselves and there's singulars of them. When there's several of them together, they start looking more like vermin than chipmunks. So, yeah. In 5 years, so maybe I should have done this at an earlier time. Oops, where did I go? Oh, in here. Okay. Where are we? Uh-oh. Oh, there we go. Yes, warts are scary. Yes, swarms of chipmunks. In 5 years, there will be, say, 300 chipmunks. Assuming no predators, because there aren't any. Well, except for the exterminators. When will there be 500 chipmunks? That's what you call the, well, probably should have called the exterminator here, but I know it's sad. Students get really mad at me. I'm like, you can't kill the chipmunks. I'm like, when there's 300 of them, you got to do something. Okay. So when will there be 500? So this is a two-part problem. All right, we have P sub t, P sub 0, e to the RT, the growth rate. And they tell us like what happens. We go from 100 to 300 in 5 years. And then they're asking, well, when is there going to be 500? Okay. And I do have a lot of students that will just say, well, you know, we have in the year 2020, we had 100, 200, 5 years later, 2025, there was 200 more. And then 5 years after that, there should be 500, right? 200 more. That's not exponential growth. It doesn't work that way. Okay, you're looking at a curve. This is if you keep adding 200, the curve you're looking at looks like this. Okay, so over a small period of time, not much change, but as soon as you get to this part, yeah, all bets are off. So okay, so let's see here. We had 300, right? After 5 years was equal to 100. E, and I don't know what the R is. It's always the case with these. Times 5. 5 years passed. So let's go ahead and divide both sides by 100. Right? So we get 3 is equal to e to the 5r. Okay. Now we have to take a logarithm. So we're going to do ln of 3 is equal to ln of e to the 5r. And this is going to come down in front because that's the whole point of doing a logarithm. Okay, and that is equal to the ln of 3. So r is equal to 1/5 natural log of 3. Okay. Now, the real problem we had is when is there going to be, right? When is there going to be 500? And Bloomsburg's actually a big campus. I don't know. It's not huge, but it's not Penn State. So we'll say 500 is equal to 100 because that's when we're starting. E to the R, and then I don't know what T is. We'll say this is RC for chipmunks. Okay, and we're going to go through and do the same thing. So we're just going to divide by 100, give myself a clean exponential function here. Is equal to E to the RC times T. Okay, taking a natural log of both sides. So natural log of 5 is equal to natural log E to the RT. This will come down in front. That's the whole point. And that is equal to the natural log of 5. We know what the RC is, right? We just solved that one. That's one. We have T is equal to natural log of 5 divided by whatever RC happens to be. Ugh, it's been a day. And RC was 1/5, right? Natural log of 3. And that is equal to T. So we'll just bust that on our calculators and be done with it. So let's see here. We have natural log of 5 divided by, I'm going to put a parentheses here. So we have 1/5 times natural log of 3. And we should be set. T is equal to 7.3 years. T20. Right? So that's population growth. That's how we do that. Um, that's a very common type of a problem for a final exam in college algebra. Okay, so we have choices of interest, population growth, and radioactive decay. Right? Let's see here. What did I do with you guys? I think I posted you guys to the bottom of this one. I did. Let's see here. Difference quotient, composition. Describe a rational function. There, we might do that one. Construct a rational function with a horizontal asymptote there we go, at y is equal to 3, vertical asymptotes at, let's go with 1, x equals 1, and x equals 5. Okay. And let's see, do I want to make it anything else here? And how about we do a y-intercept of 1. Okay. Okay. I think that's something we can work with. So, and this is not a unique answer. Okay, there's other answers we could have. So what do we know about the vertical asymptotes? Well, we know that's where the denominator is 0, right? So when x equals 1, the denominator is 0. So x minus 1, right? X minus 1 is a factor in the denominator. X equals 5 is also a 0, right? Because that's where we have another vertical asymptote. So x minus 5 is a factor in the denominator. They didn't tell me there were other ones, so I'm going to assume that there aren't. Okay, so far, what we have for our rational function here, right, is we have y is equal, I don't know what's on top just yet, but on the bottom we have x minus 1, x minus 5. Does that make sense? Now, on the top, right, what's the, if I was to multiply, I'm not going to do it, but if I was to multiply this out, what degree would the bottom be? The bottom would be a degree 2. Okay, that's x squared, right? Now, since the top has a not the top, but the horizontal asymptote has a y equals 3, the ratio of whatever's on top and the bottom has to be 3. Okay, so we're going to need an x squared because the degrees have to be the same. And the coefficient here divided by the coefficients on the bottom, that has to be 3. Okay. So there we go with that. Okay. Last piece. We know that the y-intercept is 1. So when x equals 0, y is equal to 1. Okay. So what is that going to mean? Well, if I plug in 0, the whole thing is 0, right? Because if I plug in 0 here, we get 0 on the top over I have no care what's on the bottom. So there has to be something else up here, right? We have to have a 3x squared plus something, right? Now the top isn't going to be 0. And on the bottom, we still have an x minus 1, x minus 5, yeah? And when x is 0, y is equal to 1. So why don't we just go ahead and do that? Why don't we say set x equal to 0, and we're going to get 0 plus a divided by, well, we have 0 minus 1 here. It's minus 1. Actually, let's go slow. Zero minus 1, and then we have a 0 minus 5, and this is equal to 1. Right. So here we go. We have a over, here's a negative 1, here's a negative 5. That's equal to a over positive 5, right? That's equal to 1. Ah, a must be 5. Okay, that's how this is going to work. So we're going to be able to say, well, this is 3x squared plus 5 over x minus 1, x minus 5. That's my function. Could there be a 2 here? Yeah, there could be. I don't know. Could there be a 3 here? Yeah, I don't know. That's not something that I can do. Like, I have no information to say that that's true, but I have no information to say that it isn't. So if you put an extra thing in here, I couldn't tell you were wrong. You're kind of complicating it in a way that doesn't need to be. But, oh no, you would have to leave it because then you would raise the degree. So unless you're going to raise this, you have to leave this the same. So if this was a 2 and you made this one a 3, then it would work. But simple is best. So I wouldn't start putting powers here to track powers up here. We probably need to do at least one more of those. I think your book does have some problems that do this. They're a little bit easier though. So let's work on one that's like a little bit more reasonable. So let's see, what do we have? A vertical asymptote at x equals, we'll say negative 3. Okay. And horizontal asymptote at y equals 0. Okay. Let's give it a y-intercept at y is equal to, so again, with the vertical asymptote, okay, so there's our problem. With the vertical asymptote, I know x has to be negative 3. That's my denominator. Okay, so that means that x plus 3, right, move this over, is a factor of the denominator. It might be the only factor, that's okay. But do I have any other vertical asymptotes here? No, so we're fine here. Okay, there might be other stuff, but again, simple is better because we don't want to make it too complicated to do something else later. So my bottom here is x plus 3. What about my top? Well, the y sub 0, right? That is equal to, or the horizontal asymptote of y equals 0. That means the degree of the top has got to be smaller than the degree of the bottom. Well, that's 0x, right? Because that's degree 0. This is degree 1. What's smaller? Degree 0. Okay, but we are going to have some kind of a thing up here to deal with the fact that when I set x equal to 0, we have to be equal to 2. Okay, so we have a over 0 plus 3, that has to be 2. So we have a over 3 equals 2. A must be 6. Okay, so our function here, right, that is equal to 6 over x plus 3. That fits the conditions that you were given. All right. Maybe one more, and I'll do this one so it's kind of tame as well. Okay. Why don't we do one very similar to that one? We'll say there's a vertical asymptote. And say x equals -2. There is a horizontal asymptote. Giving you an oblique asymptote in a problem like this is kind of cruel because that's the result of polynomial division. So I'm giving you the answer to the polynomial division, and you have to kind of go backwards, which is multiplication. So it's not really not that bad, but it's a lot to figure out, especially on a final exam. And we're starting to get into the realm of this. This is getting to be too complicated. Okay, so we're pretty much dealing with horizontal asymptote of 0, horizontal asymptote of something else. And we'll say y is equal to 2. Too many 2's. How about a fraction? That'll make it harder. How about a third? All right. And let's go with y-intercept of 1. All right. First thing about the horizontal or the vertical asymptote, rather, x is equal to -2. That's my denominator. So x plus 2 must be a factor. Okay. What do we know about the top? Well, we know that the degree of the top and the bottom are equal. Degree are equal. So the bottom has an x plus 2 in it. The y is going to have some kind of an x plus a here. Okay? Because this degree here has to be the same as that one. That's the only way we're getting a y equals 1 as an asymptote. Okay? And then the last thing we could do, right, is say, well, oh no, it was 1/3. So the degrees are equal, but this ratio has to be 1/3. Oh, why don't we just do that? So why don't we just say there's x plus a, and then we'll say 3. We could say 3x plus 6. We could just factor it. Or you could put parentheses here and have it work that way. Either way. But that asymptote, right, that's going to be a third. And then for my intercept, right, we're going to set x equal to 0, and then y would have to be 1. So if I set x to be 0 here, right, we get 0 plus a over 3 times 0 plus 6. That has to be 1. So we're going to get a, that's 0, over 6 is equal to 1. A is going to have to be 6. Okay, so here we have x plus 6 over 3x plus 6. That would be our function here. Okay, so when they say construct one, they're going to use some information like this. Again, keep it to a minimum. Don't go nuts, right? Of piling on a whole bunch of difficulties here. And the same thing with you guys. Like keep it simple. Don't say, well, it could be 2 here, and then I could put a 2 here, and then no, don't do that. Just leave it alone. Just make it simple, and construct your function that way. Okay, so that would be construct a polynomial or construct a rational function given some values here. All right. So I'm going to go ahead and stop recording. All right.